तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
We will start our study of groups of symmetries by looking at groups and groups of transformations and so on, specifically a class of objects called Lie groups, which are extremely useful in physics in many areas and in other parts of science as well. And I should say right in the beginning that the theory of Lie groups is a very old one, but it is still a current topic. There is still a lot of research being done in various aspects of it, and as we go ahead with physical science we discover more and more interesting connections between abstract mathematics and theoretical physics and the physical world. So this is an ongoing quest. We are not going to devote our time to a whole course in group theory or anything like that, so certainly we won't talk about abstract groups for too long, but I will talk about a few practical groups which are needed in the physical sciences, such as the rotation group and subsequently the Lorentz group, which is going to be useful in our study of relativity. So let me start by giving a few informal definitions. These are not too formal, they are kind of heuristic, and there are lots of books which would give you exact definitions of the objects I am going to talk about. The first of these is what we mean by a group, and very quickly it is a set of elements in which a composition law is defined, so that you take two of these elements and you compose them in some fashion and you get another element of the same class. So it is basically a set of elements in which some properties are specified. So the elements of the group could be A, B, C, etc., and a composition law, composition rule is defined such that A composed with B is also, these are all elements of some group G, this is also an element of G. This composition could be, in the simplest instances we are going to talk about, could be addition, or could be multiplication of matrices, things of that kind, some composition rule, okay, such that you can compose two of these elements and get another element which also belongs to the same class, okay. And most importantly you would like to ensure that there exists an identity element, A composed with E is equal to A itself, and this quantity, this object is called the identity, element. So there is a unique identity element for this class of objects such that you compose with the identity element and you get back the original element itself. And an inverse is defined. For every element there is an inverse which I will denote by A inverse, such that A inverse composed with A is the identity element. So the left inverse and the right inverse are the same, and each of them yields the identity. So this suffices to define a group, an abstract group, and we will look at examples of groups. There could be all kinds of objects. These things, the elements of this group could be all kinds of things. They could be numbers, they could be matrices, they could be operators, they could be functions, they could be any kind of mathematical object. They could be just some abstract objects in which some rules are defined. Now of course immediately there are several kinds of groups. You could have a finite number of elements or an infinite number of elements. That is the first thing that happens. You could also have an infinite number of elements parameterized by some quantity, by some parameter which takes on continuous values. So you have a continuous infinity of elements, not even countable.
Is association commutative law not necessary for the group?
For the moment we are going, this is it, and now we are going to put extra stuff on it, and then we will say what groups are, rings are, fields are, and so on and so forth. So we will talk about examples now, some simple examples. Now I am not going to talk too much about discrete groups, groups where the set of elements is discrete and the operations are discrete, but I am going to talk about continuous groups, namely groups whose elements are specified by some parameter or parameters which can take a continuous set of values. The moment you have continuity, then other notions come into play like connectedness, compactness, and so on come into play, and those are what are going to be interesting to us. In other words, we are going to talk about topological groups. So you have a group whose elements are specified by some parameter, and this parameter takes on values in some continuous set of values in some continuous region. Then we can talk about connectivity, we can talk about compactness, metric, and so on and so forth. So we will talk about topological groups without defining topological groups in too much detail, but let me give an example of a group, of a continuous group. R1, just the real line is a group, but you have to specify what operation gives you this composition and its addition. So you take two real numbers between minus infinity and infinity, you add them, you get another real number, and the identity element of course is 0 in this case, the ordinary 0. So R1 is such a group. The parameter space of R1 is of course the line, because the elements of this group are specified by specifying a point on this line, and it is clearly continuous. It is also connected, because you can go from any element to any other element by a continuous path which remains in the space completely. So this is an example of a continuous group. Not at all, not at all, does not have to be connected. Every group does not have to be connected. You could have a group of 2 elements, say. There is no question of connectedness or anything like that, just 2 elements. I have to define a composition law, Z2, the group of integers modulo 2, a cyclic group of order 2. This has just 2 elements which you could call 0 and 1, and the rule is binary addition. For every group, yes, we can always find a set of parameters. That is how I am going to specify the group always. There need not be a parameter, I could just specify the elements themselves like 0 and 1.
How do we define continuous and connectedness if it has no physical representation?
Why? Continuity and connectedness are completely mathematical terms, right? Connected means that you should be able to draw continuous paths from one point, one element of the set to another element of the set. Simply connected is another story. It means that every part should be shrinkable to a point and so on, but certainly it is connected. But you can think of disconnected sets. You could have a set of elements here and a set of elements here, and this is something else, this is outside. So this and this, within this is connected, that is connected, but it is not simply connected. This is completely disjoint sets. On the other hand, if I had this kind of parameter space with a forbidden region here, and this is my region, this set of points is connected. From every point I can arcwise connect to every other point, but it is not simply connected because there is a hole here. On the other hand, this is not even connected. Okay. So
shouldn't we define a neighborhood for that?
Yes, of course I should define open sets, neighborhood, and so on and so forth. So all the epsilon deltas we will put in when necessary, otherwise it becomes very, very abstract, and I would like to get some examples right away. So as I said, this is not a formal course in group theory, with all due respect to the rigor and things like that. We would like to use it, I would like to use it, and I think that once we start using it, then we will learn all the definitions backwards and so on. Right now what happens is, if we give all the definitions, you have a whole lot of definitions, and then I make a statement, you will have to check with the definitions whether it is really part of these definitions or not, whether it follows from it or not, and by the time you have forgotten what we are trying to prove, at least I would. So let us do this in a very heuristic way, hand waving way. This is not the way to learn group theory, you should not learn group theory. the right way to learn group theory is to take a textbook on group theory and go from the beginning to the end, and at the end of the day you have learnt all that there is in the book. It's already been done. That's the right way to learn it. The useful way to learn it is to have a physical problem for which you want to apply group theory, and you discover that's the way. So you take the book out and then you sniff through the index. You look at the index, then you say, page 67 has it. You go to page 67, then you discover there's a concept there for which you have to go to page 24. You go there, then it says to really understand what's written on 24 you have to go to page 252. So you go there, do this. In between you sort of smell the book a little bit, you get used to it and so on. Then you apply to make a few mistakes, then you look at another book where it's given right or something like that, and that way you learn the subject non-linearly. Never read a book linearly. So this guy is a continuous connected group. In fact, we can go further. Rn is also a group, because this is a set of numbers, real numbers, an n tuple of real numbers whose elements can be specified like specifying x1, x2 up to xn here, and the usual law of vector addition in n dimensions. This is a Euclidean space once I give a metric to it, but right now we are just talking about Rn. This is also a group, the set of n tuples of real numbers, in which I add the rule is again addition but component wise. So x1, x2 up to xn, y1, y2 up to yn. The composed thing is x1 plus y1, x2 plus y2 and so on. That too is a connected group, continuous group. Okay. But there are other groups which are not so simple to look at. A simple example, for instance, would be the following, and I will come back to this. S1, this is just a set of points on a circle, but now the group law is multiplication. So I take points on, say, the unit circle in the complex plane, they are of the form e to the 2 pi I theta, and I multiply e to the I theta, and I multiply two numbers by simply saying e to the I theta prime is e to the I theta plus theta prime, and it remains on this circle. So that too is a group, but that's got much more complicated properties than R1 has, and we'll see the relation between them. Okay. Now I'm going to look at groups where the elements are parameterized by one or more parameters, but the elements are analytic functions of these parameters, smooth functions, things which can be differentiated, at least twice differentiable, ideally infinitely differentiable. Any analytic function is infinitely differentiable. So I'd like to look at groups where I have, in addition to a group set of elements, I have an underlying space of the parameters, and the space is actually an analytic manifold. Well, it's actually a space where I can write these elements as analytic functions of this set of parameters. That's the kind of group I'd like to look at, and these are called Lie groups. So the elements are analytic functions of the parameters. This is important, because this immediately means that in addition to continuity, in addition to connectedness and so on, I have imposed some further conditions. I have actually said these are analytic functions, so I can differentiate them, I can ask for infinitesimals and so on. So calculus can be done using this set of elements. So this is the first step, and this was taken by a very great mathematician, Norwegian mathematician, Sophus Lie. And he lived in the 19th century from 1825 or something like that up to 1899, and in the process of his mathematical investigations he laid down the foundations of the modern theory of groups, of continuous groups. So it's got close links with topology, very close links with differential geometry and so on, which we will not get into in many of these subjects, but we will talk mainly about Lie groups, and all the groups we are going to look at are essentially Lie groups this kind. Okay. Having said that, let me point out that you can represent a group in more than one way. So let me come to the idea, a very important idea of representation of a group, and it is not to be confused with the group itself. Representation. You could always represent the elements of a group by other objects and form a rule to go from an element of the group to that other object. Then that set of objects is a representation of the group. It may be a faithful representation, in other words there may be one-to-one mapping between the elements of this group and the set of objects you are talking about, but there may be one-to-many as well. If you have a one-to-one mapping, it is called an isomorphism, and if you have one-to-many, it is called a homomorphism, and I will give examples. Let me take a representation of R1 which looks nothing like R1 when you start off. R1 is just a set of real numbers on a line, but here is another representation of R1. Corresponding to every real number A element of R1, I associate corresponding to this a matrix, let me call it L sub A, and it is a 2 by 2 matrix which is 1 A 0 1. And now the addition law here I replace by the multiplication law for these matrices, and it is easy to see that A composed with B is the same as A plus B. That is what I mean by the composition law in R1, but here LA LB is equal to LA plus B in the sense of matrix multiplication, and that is trivial to check. This is an upper triangular matrix, you multiply another one with a B and you are going to get A plus B. Okay. For every number here there is a unique matrix here and vice versa. Therefore this set of matrices forms a representation of the Lie group R1, but it is not the same as R1, these are different objects, and the rule also has been changed, but there is no problem. I could, instead of R1 I could talk about this completely, and it is a perfectly good representation. So this technical statement is this set of matrices forms a group, and let me just call it L sub A. This is actually a group. This is isomorphic to R1. There is a one-to-one mapping, and it is a 2 by 2 matrix representation of real numbers. It is not the simplest representation, but it is a representation, and everything you can do with real numbers you could as well do with this in here. Maybe not very useful very often, but it is certainly a representation, and by this symbol I mean an isomorphism. Alright, yeah.
One of the previous classes you said that Lie group is a group where anti-commutative and Jacobi identity are followed.
That was a Lie algebra. That was a Lie algebra, and we will talk about Lie algebras. Yes, indeed, it will turn out, let me anticipate a little bit, that once I say that the elements are analytic functions, I would like to write these analytic functions down, and very often they are exponential functions, and then if they are close to, if they are derivable from the identity element in a specific way which I will demonstrate, then you can generate the entire set of elements by using a set of what are called infinitesimal generators, and these generators will obey the Lie algebra corresponding to the Lie group itself. So in a sense you can replace the study of the group by the study of the Lie algebra, and this is the idea behind writing down things which are analytic functions. Okay. Yeah.
So the parameters here are continuous variables.
The parameters are continuous. Yes. If the parameters are discrete, I would have a discrete group, and I am not going to talk about that at all. Lie groups are not discrete groups, they are continuous groups, more than continuous groups, they are actually analytic in some sense, so it is a little more than that. Okay. Now the familiar groups that you do in that you look at in crystallography, like the group of symmetries of an equilateral triangle or the group of symmetries of a cube, these are discrete groups. They are finite groups, they have a set of elements which obey a certain rule. Now that group operations, the group elements are actually transformations on this geometrical object, but you can represent those transformations by other objects which are matrices in general, but there could be other objects as well. So we have to distinguish clearly between the representation of an abstract group and the abstract group itself. Very often I will not distinguish between them. I'll simply say, once you have a relation like this, I would just as well work with this instead of this. Everything that you can do here you could also do there. There are other representations of R1. Here is another. Suppose I map R1 to S1, so corresponding to every x. So I start with some x element of R1, some real number, and I put a map f such that R1 goes to S1. This is a function of x which takes me from a real number to a complex number in S1, and this map is f of x equal to e to the 2 pi I x. For every x I replace x by e to the 2 pi I x. E to the 2 pi I x is a complex number which lies on a circle, unit circle, and now the group addition law is replaced by multiplication law. I certainly have x plus y is an element of R1 here. Here it would be f of x multiplied by f of y is f of x plus y. So this is a representation, but it is not a single valued representation, because you have R1 here and you have S1 here. This, by the way, is the mathematical notation for a circle. It is a one dimensional sphere. The object is one dimensional. S2 would be the two dimensional sphere, what we would normally call the surface of a balloon in 3 dimensions. S3 would be the 3 dimensional sphere, and so on, and people have studied all the properties of Sn in general. They are not as trivial as you think, and we will see there are some deep differences between, for instance, S2 and S3. S1 is also a Lie group, R1 is a Lie group, but you see every time you increase by 2 pi, you increase x by an integer, you come back to the same point on S1. So it is clear that this point, if it is mapped here and the neighbourhood of this point is mapped to a neighbourhood here, there is a point here which is separated by an integer which is also mapped to this guy, which is also mapped to this guy, and so on. So an infinite number of points separated by integers are mapped onto the same point in S1, and that is true for every point on S1. This is a representation, however it is not a one-to-one representation, it is a homomorphism. This guy here is a homomorphism. It is not an isomorphism, but it is isomorphism is one-to-one. That means you go back, you can go back, it's get back the original thing uniquely, but that is not true here. Many elements are mapped onto one element here, and then the question is which of those elements is mapped onto the identity element here. This is e to the 2 pi I x, so let us put some coordinates on this. This is theta equal to 0, theta equal to pi over 2, and so on till 2 pi. This is the identity element here, and the identity element comes from the point 0, it comes from the point 1, it comes from the point -1, and so on. They are all mapped onto this single point here. So an infinite number of points, all the integers, are mapped onto the identity element in S1, and that set of points which is mapped onto the identity element in a homomorphism is called the kernel of this map. The kernel is the set of integers.
So representation is basically a mapping.
Pardon me?
Representation is basically a mapping.
Representation is basically a mapping, yes, but it could be one-to-one, it could be many-to-one, and so on. So this mapping, obviously if it is many-to-one, it does not have an inverse. So give me a point on S1, I cannot tell you which point on R1 it came from. I can do that modulo a set of integers. Therefore what one says is that R1 quotiented with Z is S1. This is quotiented. So the symbol is R1/Z if you quotient it. Therefore modulo an integer you can identify which point it came from. You take a point on S1, you can say where it came from in R1 modulo an integer up to an integer, you could always add an arbitrary integer to it, and the kernel is Z, and therefore when you quotient this space with this Z you get this. Now we come to this question of connectivity. Locally this thing looks like that. In a sense, if you go very close to this fellow looks like a straight line segment. Okay, I am saying this very loosely, there is a tangent here and that looks like that. So the properties of this and the properties of that are more or less the same locally, but globally that is not true. It is quite clear because then the curvature takes over and so on, and then this is not true. So although locally there is, in a homomorphism you have this mapping which looks one to one, globally it is not one to one, and there is a non-trivial kernel there. We will say something more about these kernels and so on as we go to other groups here, but this provides a cover of this for this group, in the sense that this thing here R1 is simply connected. By connectivity I mean if you took two elements of this set, you should be able to go by a continuous path from one element to the other element without leaving the set of elements. That is connectivity. Simple connectivity means I should be able to shrink all closed paths to a point without leaving the space. So I could start on this line, go somewhere, and I stay on the line, come back, and this like a rubber band could be shrunk to 0 without leaving the space at all, then it is simply connected. That is why I said if you take a plane and you puncture it, you remove a hole from it, remove a point from it, then any path which encircles this hole cannot be shrunk to 0 to a point without crossing, without leaving the space. S1 is not simply connected, it is infinitely connected, because it is clear that if I took a rubber band, it is a stretchable thing. So now what is a closed path on S1? I start here, I go there and I go back, that is a closed path, but that can be shrunk to a point without leaving the space. But the moment I go around once like this and complete the path, this path cannot be shrunk to a point. It is like putting a rubber tube around the rim of a cycle, you cannot shrink it now without tearing or cutting or anything like that. You can't smoothly deform it to a point. In fact, you could take the rubber band and put it twice round the circle, this rim, and that cannot be converted to either 0 winding or 1 winding once. You could also wind it in the other direction twice, and that cannot be shrunk to anything else. So the question of shrinking paths becomes very crucial in all these continuous spaces, and this is part of a subject called homotopy, and we will talk about the elements of this homotopy. What we are doing is kind of very crude version of homotopy here. The set of closed paths on this S1 can be put into one-to-one correspondence with the set of integers. This path or this path or this path or even something which goes all the way there and comes back without crossing can all be shrunk to a point and can be put into one-to-one correspondence with, they form an equivalence class which can be represented by 0, the number of times you go around completely. Then the set of all paths which do this once, maybe it also does this a little bit, does not matter, that can be put into one-to-one correspondence with the number 1, because that is the winding number of this map. Similarly, there is a set of parts which can be put into correspondence with -1, winding number 2, and so on, and on this side -2, this side. So the set of all closed paths in a continuous space which are deformable into each other without leaving the space form an equivalence class. And there are many equivalence classes for spaces which are not simply connected. For something which is simply connected like R1, there is just one equivalence class. Every path on this line, no matter what you do, how many times you go zigzag back and forth, you can continuously shrink it to a point. So there is only one trivial element, one equivalence class, but on S1 you have as many equivalence classes of paths as there are integers. The set of equivalence classes of a space, and let me call the space V. V is the continuous space. The set of equivalence classes forms a group and it is called pi 1. The group of equivalence classes of closed paths in V, and it forms a group. In fact, you can compose paths. You need a rule for composing paths, and it is precisely the naive rule that you would think about. For instance, if in a space you start at a point and then you have a closed path like this, that is a closed path. If I have this guy here and the space is completely simply connected, you could just as well convert it to this continuous thing, could just become this, and then it could be shrunk to a point completely. So you can compose paths, you can add paths to it, and so on. So under all these operations, finally it reduces to just a set of equivalence classes of paths, and that set forms a group, and this group is called the fundamental group. The fundamental or first of the space V. I look at, you mean how the paths on this are Z? Well, I pretend there is a rubber band which I want to put on a rigid cycle wheel, and then I ask, is it infinitely stretchable, but it is topologically deformable. The only thing is I cannot break it. Then if I start with a band here and go around like this once, this path cannot be shrunk to a point without cutting it somewhere. If I put it around twice in this fashion, that cannot be converted to something which goes around only once or which goes around 0 times without cutting it, and so on. And then I have a sense to this. Every path must have every closed path I must have an orientation. I must also have a sense in which this path is described, and if I do it in the clockwise direction or counterclockwise direction, I end up with plus or minus as the winding number. So the paths are all classified according to the number of times they wind around, and that is the set of integers. Yeah.
Kernel is just a element identity.
Yes.
Can we tell that it is isomorphic?
Then it's yes, isn't it? The identity element is connected to just one, provided provided it is connected to the identity. All elements need not be connected to the identity continuously. I will come to an example of that. This is only true if the entire thing is simply connected, otherwise okay. So it is possible there are elements which cannot be found continuously from the identity element, then this is not true. Okay. So the idea of pi 1 of V is clear. So we can write this down. Pi 1 of S1 is the set of integers. What is pi 1 of R1? What is this equal to? It is a group, but there is only one element, and a one element group is called a trivial group. It is just the identity element. You can represent it as you like. It's just got one element, so you could call it 0 if you like. Sometimes people write it in this fashion, sometimes people write it as just E. That's not good notation because this suggests that the base of natural logs or something like that, or sometimes they write it as 1 or whatever. It's a trivial group. It's a group which has only one element, and anything which has got pi 1 of whatever is just one element is simply connected. That space is simply connected. What's pi 1 of S2? What's pi 1 of S2? Some subtleties are involved here. S2 is the surface of a sphere. It is parameterized by two angles, the latitude and the longitude. It need not be embedded in 3 Euclidean dimensions. You need at least 3 Euclidean dimensions to embed it, but it need not be there. It is just the abstract space. just the 2-dimensional surface described by the surface of the usual kind of sphere. Now what is pi 1 of that? You put a rubber band on it, it is clear that no matter what you do to it, you can always slip it off. You can always slip it off, you can always shrink it to a point. You cannot lasso a basketball, that is the way it is said in colloquialism, and therefore this is equal to the trivial group. I will write it as just 0, I mean it is just the trivial group. So already you begin to see between S1 and S2 there is a deep difference. Is S2 a Lie group? I have to define an operation on it in order to compose, right. This is a point on a surface of a sphere in the conventional sense in 3 Euclidean dimensions. Therefore I can specify it by a latitude and a longitude, or I could specify it by a unit vector whose tip lies on the surface of the sphere. If I add 2 such unit vectors, do I still get a unit vector? No. So S2 is not a Lie group. It is a space, it is a connected space, it is a simply connected space, but it is not a Lie group, not a Lie group. Well, you think of any operation in which you make it a Lie group, this is not a Lie group. No, it is just a space. All spaces are not groups. There are groups which have topological groups which have spaces with specific properties. So S2 is not a Lie group at all, but pi 1 of S2 is 0, that is for sure. S3 happens to be a Lie group once again. What is S1 cross S1? Is this a group? It is a torus, it is a torus. Is it a group? Yes, yes, whatever it is for, I should really write direct product, that is for every point here you associate the full space there and so on. So it is a Cartesian or direct product, and this guy here is parameterized by one real number here on one quantity e to the I theta 1, this is e to the I theta 2, and this is a group. Is it simply connected? No, it is not simply connected. What is its fundamental group? What is pi 1 of S1 cross S1? Yeah, Z cross Z, that is it. Because you can take a rubber band on the torus and wind it around m times this direction and n times in that direction, and m and n are integers, and these paths are homotopically not equivalent. So that guy is S1 Z cross Z pi 1. But you can do the same thing that you did for this fellow, namely you can unroll this, imagine this guy here rolling on that, and then of course every point here gets mapped there many times, that is why it is a homomorphism. You can do the same thing with this torus S1 cross S1, it is called the 2 torus. This guy is T2, and this T2 is parallelizable in the sense that you can also put it into correspondence with, what is the analog of R1 that you would put it in correspondence with? R2. But on R2 you would now identify all points which in the x direction differ by an integer, all points which in the y direction differ by an integer, and what do you call that? I would call it a square lattice. I would call it a square lattice. So this guy here, once you represent it in that fashion, this torus is this plane in which you put a grid such that this point, this point, this point, this point, etc. are all mapped onto a particular point here. This is the representation of the lattice, the plane representation of T2, and it is also not a simply connected group. Okay. It is infinitely connected. What is the kernel? What is the kernel of this group? What is the kernel of this mapping? Yeah, m comma n, the set of pairs of integers. All those numbers go on to a single point, the identity element in T2, okay, and so on. You can generalize that S1 cross S1 cross S1 an arbitrary number of times, and it will get give you a representation of Rn, okay, not a single valued thing, it is a homomorphism. So we have seen, oh, here is one more representation of R1, a representation in terms of functions. So I could do the following, I could say, just as if A is an element of R, let me look at the space of all infinitely differentiable functions of a real variable. So every function f of x, where x is a real variable taking values from minus infinity to infinity, and I assume that this f of x is a function which has an infinite number of derivatives, like e to the x or sin x or cos x or something like that, and then I put a rule saying that this quantity A is represented by an operator T sub A, so it is now a representation by an operator such that this is equal to f of x plus A. So it shifts the argument x by x plus A. Then what is the group composition law? It says T A, T B, f of x is T A acting on f of x plus b equal to f of x plus a plus b. So just as A and B gave you A plus B on R1, this is the operation, this guy here, that's it. This is a representation, this T sub A. Now of course you would say, what does it look like? What does this representation look like? I do not care, I just tell you that TA is an operator such that it acts on the function f of x and shifts its argument by an amount A. But why do I need that it should be differentiable an infinite number of times? Why do I need that? Because I also have in the back of my mind the fact that I can write this f of x plus A in terms of f of x in a Taylor series provided all the derivatives exist. So you know this can also be written as e to the A d over dx on f of x, where this is 1 plus A d over dx plus A squared over 2 factorial and so on. So I need an infinite number of derivatives to act on that, and then I have an explicit representation of this operator. So this operator is represented now by a differential operator, but an infinite order differential operator. So I started with a humble real number A, but I am now representing it by an infinite order differential operator. So in the space of functions there is a representation as well, and sometimes this might be very useful. This is called this when you want to move an object, what do? You give it momentum, right? So what I have done is, if this were a wave function in quantum mechanics, I have translated it by applying momentum to it. So this is the reason why the momentum operator would be represented by minus IH cross d over dx in quantum mechanics. This is the underlying reason. We are going to put some more conditions on it, like real eigenvalues and so on, but ultimately it is just this. This is the reason for it. So here is a representation TA. Then we had a representation in terms of L sub A and so on. So many ways of representing the same thing. That is the moral of the story. And you must not confuse representation with the group itself. That is an abstract set of objects. Now the kind of things we are going to do is to look at groups of transformations of some geometrical objects, such as a plane or 3-dimensional space or any linear vector space of some kind. And the whole of quantum mechanics in fact could be regarded as transformation theory. In fact, when Dirac first evolved quantum mechanics in its modern form, he called it transformation theory. That is it, for want of a better word, and it was a very good word, very good phrase. So we are going to look at groups of transformations of geometric objects like planes, for example. Let us look at the simplest of these. Let us look at rotations on a plane. Okay. This will bring us to grips with something. So I have a plane, the xy plane, and I am going to look at the set of rotations of the coordinate axes. So from x and y I am going to go to new coordinate axis x prime y prime by the usual rule, which is x prime equal to, so I will write it in this form, equal to cos alpha sin alpha minus sin alpha cos alpha on xy. Okay. So what I have done is to go from xy to x prime y prime through a rotation. This is equal to some rotation acting on xy. So this is my group element, the abstract act of rotating the coordinate axis, the abstract rotation of the coordinate axis. This is a representation of that rotation, because I have chosen to represent a point in the plane by a column vector of this kind, but I needn't have done that. I could have chosen some other representation of R2 plane, then I would have another representation of the set of rotations. So is this clear, that there is an abstract rotation which takes a point on this plane to another point on the plane, leaving the origin unchanged, but if I write this point on the plane as column vectors in this fashion, this provides a representation of this R. It is a 2 by 2 matrix representation. I can give you a 3 by 3, I can give you an n by n, I can even give you a 1 by 1 matrix representation. I say that all rotations are represented by the unit element 1. It is a trivial representation, it is not going to do very much for you, and it is not certainly an isomorphism. But here this set of rotations is most conveniently represented by 2 by 2 matrices. Now what you have to tell me is this unique? For every rotation do I have just one matrix? Pardon me? I could have 2 pi plus alpha. Suppose I say alpha runs 0 to 2 pi, then this is unique. So I have to put some conditions on alpha. If I say 0 to 2 pi, then that is it, it is a unique thing. Now let us see what this actually implies. This set of rotations means that the distance, any rotation is a linear transformation of this plane which takes you to some other axes x prime y prime, such that distances are kept unchanged and this point is unchanged. It is homogeneous in the sense that the origin remains the origin, so no addition of constants, otherwise it is both a rotation as well as a translation. That is a different story altogether. That also is a group, but it is a different group altogether. This is a linear homogeneous transformation Is it invertible? Yes, indeed, this rotation can be inverted. Certainly it can be inverted. There is an R inverse for every R and distances are kept unchanged. And what is the condition that ensures that distances are kept unchanged? That the transformation should be orthogonal, that is sufficient. On the reals, that is sufficient. So I know that R, so if I write it as, let me call this R of alpha. This is my abstract rotation, this is the 2 by 2 matrix representing the rotation. Then R transpose, so let us write it even better, R of alpha, R transpose of alpha is equal to the identity matrix, which corresponds to the identity element of the rotations, which means no rotation at all. This is also, by the way, equal to R transpose alpha, R of alpha, and that says R transpose of alpha equal to R inverse of alpha, and it is a trivial matter to verify that this is R of minus alpha. After all, an inverse rotation means you go in the opposite direction, you change alpha to minus alpha, sin alpha changes sign and cos alpha remains unchanged. So this is the group composition law written in terms of 2 by 2 matrices in this fashion. This set of matrices forms a group, that group is the orthogonal group of orthogonal matrices in 2 dimensions. O2. But now I ask, what is the determinant of this matrix? From this guy it is clear that the determinant, the moment I say a matrix is orthogonal, it means the determinant of this matrix, its square is equal to 1. So I can only say that the determinant is plus or minus 1. So the group of 2 by 2 orthogonal matrices is not quite giving you these rotations, because the group of 2 by 2 matrices has matrices which have determinant minus 1, and they cannot be formed continuously from the rotation here. They would correspond to something where the x axis is flipped, they would go to a left handed coordinate system. So this contains, this is a group no doubt, but it contains more than the representation, more than the rotations. It contains rotations as well as reflections. If however I write this, which means that this is a special orthogonal group in 2 dimensions, those matrices which have determinant plus 1, then this forms a group which is a subgroup of O2, and this set of elements is in 1-to-1 correspondence with the set of rotations, and you can form this set of elements continuously from the identity. Okay. So you already see that O2 is a bigger group than SO2, and it is the SO2 which are proper rotations. Otherwise O2 contains some improper rotations as well. They could represent the group of not only rotations but also reflections about either of the axes. Pardon me? O2 is not a continuous group. There are portions in it which are a different set altogether. Now what so we will have to ask, what kind of matrices are those guys, the remaining matrices, the ones which are in O2 but not in SO2. That is not very hard to find, so we are going to do that next time, and then we will take this up to SO3 and see what happens, and SO3 you will see will become considerably more complicated for the following technical reason. This group is abelian in the sense that if I rotate by alpha and rotate by alpha prime, it is the same as rotating by alpha plus alpha prime, and I could have done this in either order, but the moment I have rotations in 3 or more dimensions, then if the rotations are in different planes, they do not commute with each other. So all the complications arise because in higher dimensions rotations about different planes do not commute, the order in which you did this matters, and they form what are called non-abelian groups, and this will bring us the idea of generators and the Lie algebra and so on. So we will do that next.